Yep. Okay. I'm going to start now, though, okay? Okay, so no one's watching right now, so I'm going to start going through some email questions that people sent in hopes that you will be reviewing these things at a later time. So let's pull them up. Okay, so the first question comes from Ryan. Can you do a quick review on the tests and how to determine when to use which tests? So this is something that we did yesterday in the in-person review. So I'll just quickly review kind of all the tests that we talked about in class and when you would use each. So we start at the very beginning. We have a z-test. So a z-test, remember, is, get my tablet set up right. A z-test is when you have one sample and one population. Right? And the information you have for this is both mu, which is the population mean, and sigma, which is the population standard deviation. So you need both of these in order to do a z-test. So an example of that would be the national average on the SATs is 500. So this is all high school students in the country. They have an SAT score of 500. I have a sample of like one town, like New Brunswick, of students, and I want to know if their scores are significantly different from the population. So then you would use a z-test in that case, if you have the required information. Population mean and standard deviation, then remember that z equals your sample mean minus the population mean divided by the true standard error of the mean, which just equals sigma divided by square root of n. So the square root of n comes from your sample, sigma comes from your population. This m is your mean of your sample, mu is your population standard deviation. So that would be a z-test. You need both those pieces of information. Moving on from there, and kind of building off of that, we have a one sample or a single sample t-test. So this is very similar to the z-test where you have one sample and one population. And here you need to have mu, again, which is your population mean, but sigma is unknown. You don't have it. If you had it, then you would just do a z-test. But since you don't have it, that's when you would use a single sample t-test. So in this case, you have t equals m minus mu over the estimated standard error of the mean, where that equals the standard deviation of your sample divided by the square root of n minus 1. So again, m is your sample mean, mu is your population mean, and you divide that by your estimated standard error of the mean, which is your standard deviation from your sample divided by the square root of n minus 1. An example of this would be, again, very similar. I have a national average of SAT scores, and the average is 500. I don't know what the standard deviation is for that. I just know that the average is 500, and I want to know if my town of New Brunswick, if their high school students have a significantly higher or lower SAT score from the population. So you're comparing the means of two groups where one is a sample and one is a population. And you only have the population mean, not the standard deviation of that population. So that's a single sample t-test. So I'm trying to kind of go in order of how they were taught in class. So we did z-test, we did single sample t-test, and then next we did independent samples t-test. So this is the next one. So kind of building off of that, but instead of having one sample, one population, here you have two samples and no population. So you can also think of it as you don't have mu or sigma of the population, so none of that information is available to you, so you can't compare to the population. So now you can only compare to some other sample. And remember that the equation for this is t equals the mean of one minus the mean of the other divided by the standard error of difference. And the standard error of difference is the square root of the standard error of the mean for group 1 squared plus the standard error of the mean for group 2 squared. And just to refresh, the standard error of the mean is the standard deviation divided by square root of n minus 1. So here, for each sample, you have to calculate the standard error of the mean for that sample, and then you use both of them to calculate the standard error of difference, and you use that in your equation for t. So you use the mean of each group and the standard error of difference to calculate t. And what does this say? Well, under the null hypothesis, it's saying that there's no difference between the two groups, right? So what does that mean? That means that m1 minus m2 is 0 if the null is true. So there's no difference. And difference, I mean mathematically, there's no m1 minus m2 equals 0. There's nothing left over when you subtract. So the standard error of difference is this distribution centered on 0, where 0 is no difference. So you have all of your observations in this distribution, and you have, some critical value out on either side where 95% of observations lie within. So if you have a difference that's out here or out here, then you can reject the null hypothesis and say, actually, there is some difference between these two groups. So that's the idea of the independent samples t-test, is that you have some null hypothesis that there's no difference, and so your standard error of difference is that variance of that distribution here. So about 2 SEDs, 2 standard error of differences away, is where you would start being able to reject your null hypothesis. So that's independent samples t-test. So far, all 3 of these tests, what kind of data did you need to do them? Well, you would need interval ratio data, right? You would need some sort of continuous variable where you can calculate means and standard deviations, something that like height or like weight, where you can measure it down to hundreds of thousands of decimal places, some continuous variable. But then after we did independent samples t-test, we moved into something a little bit different that doesn't require interval ratio data. We did chi-square, or you might see it like this. So this is when you have nominal data. You can also think of it as count data, where you are placing a whole person or a whole observation into some sort of bin. So an example of this could be like, I want to know if there is some effect of gender on the type of music that people consider their favorite. So I have men and women. And let's say there's 3 different genres of music. Rap, rock and roll, and I don't know, punk. So then you would go to each person, man or woman, and say, okay, man, which one of these 3 is your favorite? Oh, I like rap the best. Woman, which one of these is your favorite? I like rock and roll the best. Other man, which do you like the best? I like rock and roll. And so you count up all these people as they exist in each genre. And what you're testing is, does the distribution of all these scores in these different bins, is it different from kind of even distribution? Kind of what you would expect under the null, where the null is gender has no effect. So let's say that there were, let's make this easy, let's say that there's 60 men and 60 women. Then you would expect, if there was no effect of gender, which is what the null is saying, then you would expect 20 men to like rap, 20 men to like rock and roll, 20 men to like punk, 20 women to like rap, 20 women to like rock and roll, and 20 women to like punk. So here you have an even spread of your 60 participants in each gender across the 3 bins that are available. That's what's expected. That's what, if the null is true, these are the observations you would see. And so you collect some data, right? You get some count of men and women and which bins that they fall into, and then you're testing to see if your observed data is different from the expected data. Sorry, I have my Amazon Echo is picking up on our chi-square conversation. So the null here is observed data equals expected. Or actually, it's the frequency of observed equals the frequency of expected is the null, or H0. So see how it's different from doing a t-test or a z-test where you're comparing means. All 3 of those tests, you're comparing one mean to another, either a sample mean to a population or a sample mean to a different sample mean. Here, you are comparing observed data to data you would expect to observe if the null was true. So that's chi-square. And remember, chi-square is observed minus expected over expected. For each cell. Okay, so continuing on with the review, and obviously once this is posted on YouTube, which it will be after the stream is done, it does it automatically, probably within like an hour. You can pause and take as much time as you like on these, but I want to make sure we go through everything first. And then we can always back up and do a practice one or whatever you'd like. Okay, so then we have the first exam. And then after the first exam, the first thing we did was correlation. So correlation, again, is different from z-test and t-test because you're not comparing means, but what you're comparing are 2 variables to see if they vary similarly or if they vary in some related manner. So it could be either as one goes up, the other goes up, or it could be as one goes up, the other goes down. But in some consistent manner, do they relate to each other? And so the way you calculate that, you calculate Pearson's R, the little r, equals the sum of zx, so that's your one variable, times zy, being your other variable, divided by the number of pairs of observations you have. So the way that looks, like we did an example in recitation, it was like height, which I'm not going to spell because I always spell it wrong, and speed on some like race. And so you'll see like people are like 60 inches tall, 72 inches tall, maybe 68 inches, 70 even, 64 inches. You know, you have a bunch of people who are all different heights. And then you have their speed as measured by like time to complete a race. TTCR, let's call it that. So this person, it took 20 seconds to complete the race. This person, it only took 10 seconds. This person took 15 seconds. This person took 11 seconds. This person took 15 seconds as well. This person took 8 seconds, and this person took 7 seconds. It's a very short race. So these are just the raw scores that you are measuring. And so you have inches and seconds. So how do you compare inches and seconds? It's very difficult to do that because they're in two different units, right? Inches is a unit of measurement of height or size. Speed or time is a measurement of length of time, right? Like you can't just say, oh yeah, they're together. So what you have to do is you have to convert all of the scores into z-scores. Now this will be given to you on the test. You don't have to actually make the z-scores yourself, but remember that a z-score is x, which is the actual observation, minus the mean of that group divided by that group's standard deviation. So what does that mean? That means that you're taking your raw score and you're converting it into a distance away from the mean in units of standard deviation. So you're saying if you have a z equals to 1, then that raw score is 1 standard deviation away from your mean. So just to kind of make some toy numbers in here, let's say the mean is 65 and the standard deviation is 1. Now I don't know if this is true, I'm just making these numbers up. You could take 60 and do 60 minus 65 divided by 1. So that's negative 5 divided by 1 equals a z of negative 5. So in this scenario, where the mean is 65 and the standard deviation is 1, you're saying that a score of 60 is 5 standard deviations below the mean. And you do the same thing for speed. And so now you have two sets of observations that are now all in the same units. So distance from the mean in units of standard deviation. So that's how you can then calculate the correlation. So you would then multiply. I get this question a lot in recitation whenever this comes up. And correlation is important because it's used both by itself when you want to find a Pearson's R. It's used in paired samples t-tests. And it's used in regression. So it's important that you feel very comfortable calculating correlations because it's used in multiple other tests. So remember, let's say we have height and speed, and I have kind of the z values for each, right? So assume I've been given z values, and I have things like 1.1, 0.6, negative 0.5, negative 1.3, and for speed I have 1.4, let's say 0.2, negative 0.8, and negative 1.2. Okay, so what you would then do to calculate R, and I just want to make sure this is crystal clear. The first thing you do is you multiply, so you have to multiply zx by zy. So 1.1 times 1.4, let me just take out my calculator so we can do it. 1.1 times 1.4 equals 1.54. So this is zx times zy. This is 1.54. 0.6 times 0.2 is 0.12. Whoops. I lost my sketchpad. There we go. 0.12. Negative 0.5 times negative 0.8 is 0.4. And then negative 1.3 times negative 1.2 is 1.56. right? So we've done the multiplication across. That's this part, zx times zy. Then you have to add up everything. So it's 1.56 plus 0.4 plus 0.12 plus 1.54 equals 3.62. So that's this part. You've now added them all up. And then you divide by the number of pairs. So 3.62 divided by number of pairs, which is 4, right? 1, 2, 3, 4. So that divided by 4 gives you an R. This equals R of 0.905, which you would round to 0.91. So, things to know, R cannot be greater than 1 or lower than -1. So if you get an R of something that's bigger than 1 or more negative than -1, go back and check your math because something is wrong. That should be a red flag. There should be no R's that are greater than 1 or smaller than -1. So here we got an R of 0.91. The next thing you would do is find the degrees of freedom, which in correlation is m-2, or number of pairs minus 2. Look up the critical value in the table for R, and then compare your value to the critical value. And then from there, you would make a hypothesis statement like we fail to reject, or we reject the null hypothesis, and why. So that's correlation. And I went through it kind of in depth off the bat because it's involved in a lot of other things that we do, so make sure that makes sense. Okay, so that's correlation. Then after correlation, we did paired samples t-test, which is extremely similar to independent samples t-test, except for having to add a correlation. So then we did paired samples t-test. So again, this is t minus m1. T equals m1 minus m2 divided by the standard error of difference. So again, you're comparing two groups that have means and standard deviations. So the SAT scores of the high school students in New Brunswick versus the SAT scores of the students at high school in Edison. Two samples with means and standard deviations. So the difference here is that the SED calculation is a little bit different. I mean, it's very similar, but there's just an extra part. So the standard error of difference equals SEM1 squared plus SEM2 squared minus 2 times SEM1 SEM2 R. So here, the first half is what you have from just regular old independent samples t-test, and then the other half is what's new. So what happens? When you have a correlation, when this value is not 0, then you have a whole number that's going to lessen the sum of the square of the standard error of the mean squared 1 plus the standard error of the mean for group 2 squared, right? This whole part is going to make this part smaller. The bigger the correlation, the smaller it makes it. So that means that if you have a correlation, your SED will get smaller. And if your SED gets smaller, that means that your T is going to be bigger. Now I'm assuming that everything else is being held constant. Your mean difference is the same. But all things considered, if two groups are related, they have a correlation that's significant, then it's going to be easier to find a difference between those two groups because the variance is smaller. Your SED will get smaller. So that's kind of a conceptual thing to think about with paired samples t-tests. What would happen if you had two related groups, but you ran it as if they were independent? It would be harder to find a difference between those two groups because your variance would be bigger. You're not taking into account that there is some shared variance between those two groups. So when would you use that? You would use it when you have two samples, no population info, two samples with means and standard deviations, and that you either have a correlation that's given to you, like you say that they are related, and here's the Pearson's R, or you had a bunch of z values and you had to calculate Pearson's R, and you found that that Pearson's R was significant. If you calculate a Pearson's R and it's not significant, as your calculated value does not pass the threshold, your critical value, then don't use it. That just because you can calculate an R doesn't mean you should use it in a paired samples t-test. It has to be a significant correlation. You have to reject the null hypothesis, which is that there's no relation. So first you say, I reject the null hypothesis. There probably is a relationship between these two groups. And then you can move on and use that R in your paired samples t-test. So after that, we did ANOVA. We did one-way and two-way ANOVA. So ANOVA stands for analysis of variance and is very important. ANOVA, ANOVA. Analysis of variance. So in ANOVA, ANOVA is kind of like a t-test, but if you think about t-tests, you always had two groups, right? So going back to my SAT example, and I'll put this in a big parentheses because this is not ANOVA, you have New Brunswick, whoops, not M. You have New Brunswick and Edison, right? I want to know if the SAT scores are different from students in these two school districts. The other way you can think about this is that there's one IV, which is like school district, with two levels, New Brunswick and Edison. Right? So you're doing it's kind of like doing a one-way ANOVA with two levels of your IV. That's how you're doing a t-test. But what ANOVA is really strong for is that you can use independent variables that have more than two levels. So let's say New Brunswick, Edison, Piscataway, and I don't know, Metro Park. So now I have one IV with four levels, New Brunswick, Edison, Piscataway, Metro Park. And I want to know if SAT scores are going to be different within these. So that would be somewhere where you'd want to use an ANOVA. Or let's say I have a drug. Like let's say I have like Advil. And I want to know if Advil has some effect on like headache pain. You can use different levels of Advil, like 5 milligrams, 10 milligrams, 20 milligrams, and then ask people to rate their headache pain. So let's say this person had a headache pain of 10, this person had a headache pain of 8, these people had a headache pain of 6. And this is like the average. Another place you'd want to use an ANOVA. So the main test for the ANOVA is the F test, where F equals the mean square between divided by the mean square within. That's how you calculate F. And then the mean square between equals the sum of squares between divided by the degrees of freedom between. And the mean square within equals the sum of squares within divided by the degrees of freedom within. So the sum of squares are given to you, and the degrees of freedom you have to calculate. Degrees of freedom between equals k minus 1, where k is the number of groups you have, or the number of levels within that IV. So like for that Advil example, it'd be 3 minus 1, so you'd have 2. Degrees of freedom within is your big N, capital N, which is all your participants, all your unique participants, minus K, where in this case it's the total number of cells, or the total number of unique combinations of things. And this will come up as more important when we do a two-way ANOVA, to be able to correctly count how many cells or how many unique combinations of IVs you have. So you calculate your degrees of freedom between and degrees of freedom within. You can then calculate your mean squares between and your mean squares within, and then you can calculate F. Once you calculate F, you then find the critical value of F using your degrees of freedom to compare your value to the critical value and decide if there is some overall effect of your IV. Now, if you have 3 or more levels, the F only tells you that there is some effect of your IV, but it doesn't tell you at which levels is there an effect. So if you are in my recitation, you'll be sick of this example, but if you think of height and grade, where I want to know if the grade I'm in school predicts my height. There's my height, here's my frequency, and then I have 3 distributions, right? I have first graders, 8th graders, 8th, and 9th graders. Right, so just by the way I drew it, you can tell that, well, maybe there's some overlap between 8th and 9th graders. So I don't know if they're different, but maybe they are. So in this case, since I have 3 levels, right, so grade is my IV, and height is my DV. Let's say I get a significant F, and that says that grade can predict height. Well, okay, well, that's fine, but is it that first graders are shorter than 8th graders and 9th graders? Is it that 8th graders are shorter than 9th graders? Who is shorter than whom in this example? So that's where you have to calculate everyone's favorite, Tukey's HSD on a significant difference. And it will generate a number, some value. If the mean difference of your levels is greater than the value you calculate for Tukey's HSD, then you can say that those 2 levels are different from each other. So to calculate Tukey's HSD, it's a crit value that you look up in the book based on your degrees of freedom for mean square within times the square root of your mean square within divided by little n, where little n is the number of participants or number of subjects in the level. So it's not big N, it's not your total number, it's the number within the cell. So that's how you calculate Tukey's HSD, and that'll give you some number. Let's say it's 5 inches, right? Because height, we'll say, is measured in inches. And now what you have to do is you have to take the mean of 9th grade minus the mean of 8th grade. Gives you some number. Let's say it's 3. The mean of 9th grade minus the mean of 1st grade. That'll give you some number. Let's say 8. And the mean of 8th grade minus the mean of 1st grade equals some number. We'll say it's 6. So that means that here, 9th graders are on average 3 inches taller than 8th graders. Here, 9th graders on average are 8 inches taller than 1st graders. And 8th graders on average are 6 inches taller than 1st graders. That's what these numbers are. And we have a Tukey's value of 5. So this number is smaller than 5. So we would say we cannot tell the difference in height between 8th graders and 9th graders. We can't tell if these are different. Here, 9th graders and 1st graders, this is bigger than your Tukey's HSD, which is 5. So we would say, yes, 1st graders are shorter than 8th graders. You can say that. And here, since 6 is bigger than 5, you can say, yep, 8th graders are also taller than 1st graders. So here, using my Tukey's HSD, first I found F. F said, yes, there are differences in height based on grade. Okay, great. And now I calculated Tukey's, I calculated my mean differences, and I can say first graders are significantly shorter than ninth graders, and first graders are significantly shorter than eighth graders, but eighth graders and ninth graders are probably not different in height, given the data that you have. If you collected more data and you were able to more closely identify the means in regards to their variation, so you minimized your sum of squares within, or you further maximize your sum of squares between, then maybe you would be able to parse out some difference between eighth graders and ninth graders. But given the data that you have, you can't determine that difference. So that's kind of the general workflow for ANOVA. I'll touch upon two-way ANOVA, but it's very similar. So two-way ANOVA is a little different because now you have two IVs, right? So moving on to two-way ANOVA, which means two IVs. So let's say IV1 equals grade, and IV2 equals gender. Let's not use gender. Let's use grade and I guess gender's fine. Gender. And so we'll say we have 2 levels of gender, male, female, and 3 levels of grade, first, eighth, ninth. You would call this a 2x3 ANOVA, ANOVA, right? So each number you have represents an IV. So I have 1, 2, so I have 2 IVs. And the actual value of that number is the number of levels of that IV. So here the 2 is gender and the 3 is grade, because I have 1 IV with 2 levels and 1 IV with 3 levels. So that was that question was on the second exam in a few different ways. So that's how you read kind of this notation, what that means about your setup. Okay, so let's say we have that. Now, how many F tests do you have to do with a two-way ANOVA? The answer is 3, because you have to do a main effect test for each IV, then the interaction. So I have an F for grade, I have an F for gender, and I have an F for grade by gender interaction. So 3 Fs. What that means is you need a mean square between for grade divided by mean square within, which will be the same. You need a mean square between for gender divided by mean square within. And then you need a mean square between for the interaction. I'll just put G times G divided by mean square within. So those are your 3 F tests. After that, you have to calculate all these mean square betweens. So you'll be given like a sum of squares for grade. You'll be given a sum of squares for gender. And you'll be given a sum of squares within. Those will be your givens. So then you have to calculate degrees of freedom for each. So degrees of freedom for grade is the number of levels of grade minus 1. So 3 minus 1 equals 2. Degrees of freedom for gender is the number of levels of gender minus 1. So that's 2 minus 1 equals 1. And then the degrees of freedom for the interaction is the multiplication of the previous 2 degrees of freedom. So here, degrees of freedom of G times G equals 2 times 1 equals 2. So now you have all your degrees of freedom, so you can calculate all your mean squares you need, and then you'll do the F tests. So you'll compare your value to some critical value based on the degrees of freedom, and then make some hypothesis statement. Either you reject or you fail to reject your null hypothesis, and then move on to your interpretation. So the thing about ANOVA is that you have an interaction and you have 2 IVs, so you have to consider all of those. So you would use that in terms of this type of data. Okay. So then we had exam 2, and after exam 2, we just moved on to regression. So up until now, you've been doing things like, I want to tell if these things are different or not different, right? The null has always been, the kind of goal has always been, say something about the null hypothesis. Either you can reject the null hypothesis, that your data doesn't support the null hypothesis, or you can't. You have insufficient data to reject the null hypothesis is typically what happens. Regression is different. Regression is you want to make predictions about future cases given the cases you have. So let's say I have height and weight. So I have two variables, height and weight. And I gather some data from people. I measure their height and I measure their weight. So each point here is a person. And from that, I can generate some equation for a line. Right? So this is what we do in regression. We make a linear model. We make a model of a line with an equation that equals y equals bx plus a plus epsilon, which is your residual, so the error that exists. Now, you're not going to be calculating that, so right now you don't have to worry about it, but I always bring it up because it's important to know that it's there. So bx plus a, right? B is your slope, a is your y-intercept, and x is your x value. So let's say some new person walks into the room whose height equals 62 inches. What is their weight? Can you please predict what their weight would be, given the data that you have? So you use the data, you generate an equation of the line, and then you would plug in that 62 inches here as x, and you would spit out some value of y, which is weight. See, because this is the y-axis, and this is the x-axis. So that's like the idea of regression, that you're making a prediction about some future case, given a pile of data that you already have. So, right, okay. So we did both simple regression, which is just one IV, one variable, and then we did multiple regression, which is two. So kind of the workflow for a question like this is one, is X correlated with Y? Is your predictor correlated with your outcome? It should be, if you want to make a prediction, right? If you want to predict weight based on height, there should be a relationship between height and weight. If I want to predict a person's weight, and the only thing I have is how hot or cold it is outside, well, that doesn't give me any information about the person's weight. So the best thing I can do, and you'll see mathematically, is just use the average weight as the prediction of their weight, because your x is not giving you any value. But anyway, first you do a correlation, right? So that means find little r. Okay, and then after that, you want to, and I'm just pulling out my textbook here because I want to make sure that I give you the right workflow. Right, so then you have to find your slope and your intercept. So b is what? It's r times the standard deviation of y divided by the standard deviation of x, and a equals the mean of y minus b times the mean of x. Right, so first you find y, and then you find b, and then you find a. And then you assemble it all together into y equals bx plus a. So you take your correlation, you multiply it by the standard deviation of y, divide by the standard deviation of x. That gives you a slope. And then your intercept is the mean of y minus b times the mean of x. So what happens if r equals 0? Your predictor is not related to your outcome. That means that, so if r equals 0, that means that b equals 0, right? Because that times anything is 0. 0 divided by anything is 0. So that means that then this is 0. And the only thing you're left with is a equals the mean of y. So you get y equals 0 times x plus the mean of y. Whoops. Plus the mean of y. That just means y equals the mean of y. So that's why, no pun intended, if your predictor is not correlated with your outcome, if it's not giving you any sort of information about the relationship there, then the best prediction you can make is the mean of y. Oh, it's 45 degrees outside. How much does that person weigh? Well, the only thing I can say is they probably weigh the average weight for people, which I don't know what it is now, what, 165? Airlines know better than I do. So that's simple regression. And then multiple regression has a few more steps, but it's also the last topic. So you would expect the last topic in the class to have the most steps, at least I would, and in this case it does. So multiple regression. So here, now, in the real world, multiple regression is used all the time, and they'll typically put lots of predictors. The more predictors you have, the harder and harder and harder it gets to do by hand. So you'll only ever see it with 2 IVs or 2 predictors. So in this case, first thing you have to do is find all the correlations. And I say all because now there are 3. There's the correlation, so R, of your first predictor with y, so R, x1, y. There's R and your second predictor in y, R, x2, y. And the correlation between your 2 predictors, so R, x1, x2. So let's say I have height and gender as my 2 IVs, and I want to predict weight. Well, height and gender are correlated, right? Are they correlated? Yeah. Gender is a bad example because gender is binary in this case. But anyway, you need to find the correlation between your 2 predictors as well as the correlation between each individual predictor and your outcome. That's the first step. If one of your correlations with a predictor and an outcome is not significant, right? Because you have to do the same thing you do with correlation. You find R, you compare it to a critical value, you make a hypothesis test, and you make some conclusion. If you fail to reject the null for one of these 2, for this one or this one, then you would move on to simple regression. You'll really only have one predictor, right? The other one's not correlated with the outcome. So it wouldn't make sense to do multiple regression. If the correlation between your 2 predictors is not significant or does not supersede some critical value of R, then you would still move on. So you would still keep doing multiple regression because you still have 2 predictors that are correlated with your outcome. So it's not just if you reject any null hypothesis, if you fail to reject a null hypothesis with any of your correlations, you do simple. It's only if your predictor outcome correlation for one of them is not significant. So you have to think about which one and then respond accordingly. But let's say they're all significant. You reject the null for all 3. The next thing you have to do is then calculate your multiple R, which is a big capital R. And that equals the square root of rx1y squared plus rx2y squared minus 2 times rx1y, rx2y, rx1, x2. This is all under a square root, divided by 1 minus r x1 x2 squared. So that's multiple r. And what that's telling you is how both IVs together, not accounting for the overlap, correlate with your outcome. And you want to do a significance test for this. But the problem is there's no critical values for multiple r. So you have to convert it into an f. And that equation is f equals r squared times n minus 3 divided by 2 times 1 minus r squared. So you convert your multiple r into an f, and then that gives you something that you can compare to a critical value. So you then take your f, compare it to a critical value of f using degrees of freedom, and in this case, your degrees of freedom between is always going to be 2, which is this 2, and your degrees of freedom within is always going to be n minus 3, which is this n minus 3. So you use those to find your critical value of f. You compare the critical value to your value, and if your value of f exceeds the critical value of f, you would reject the null and say that my predictors are significantly correlated with my outcome. Okay, and you need that to then move on. So then, step 4 is calculate B1, B2, and A. Because you want to eventually make your equation y equals B1 x1 plus B2 x2 plus A plus epsilon, which I'll always add. Right? So you have to calculate B1, that's going to go with x1. You want to calculate B2, that's going to go with x2, and then A. So that's multiple regression. I want to go through and check. So those are all the tests, and those are all the tests and when you would use them. Okay, so let me check other questions, and then we will address those. Okay, so now I'm looking at questions from about Fisher's Z, simple linear regression. Why does the numerator always equal 2 in multiple regression? And what would be the denominator? Okay, so let's go through some of that. First of all, Fisher's Z, Fisher's Z, I think you should, instead of going over step by step, I'm just going to say you should go over the conceptual part of Fisher's Z. So go through your textbook and think about Fisher's Z. I don't think it's worth spending time on doing a question step by step. I think time is better invested elsewhere on that right now. So we'll just go from there. So simple linear regression, I did kind of a skeleton example of. So really it's just find the correlation and then use the standard deviations to find B and then the means to find A. So like, for example, let's find one in the book. Which is chapter 14. Okay, here. So like in chapter 14 in the hard textbook, I think it's chapter 12 in the soft textbook. So on page 416, there is an example that's kind of all done for you. So I'll say page 416 in the hardcover book, where they say R for your predictor and outcome is 0.55. This is R, X, Y. They have Standard deviation of x equals 3. Standard deviation of y equals 3 as well. The mean of x equals 68. And the mean of y equals 70. So for on an exam, you would expect this information to be given to you, the means and the standard deviations. You maybe be asked to calculate means. You'll at least be given standard deviations. R, you could either be given, or you'd be given a bunch of z values and have to calculate R, but you should be able to do that. So anyway, with all this information, then you can calculate. So R is given, and we know that it's significant. So we can say we reject the null hypothesis. X and y are correlated with each other. Okay, so then we know that y equals bx plus a, right? B equals r times sdy over sdx. So that just equals 0.55 times 3 divided by 3. So b equals 0.55. Right? 0.55 times 3 divided by 3, those just cancel out, so b equals 0.55. Okay, now we can calculate a. A equals the mean of y minus b times the mean of x. X. So a equals the mean of y, which is 70, minus 0.55 times the mean of x, which is 68. So that equals 32.6. So all these numbers, this is an example that's kind of done for you. It's in a blue box. I would recommend going through the chapters and working through all of the examples that are in these blue example boxes, because then you can test your math against the answers step by step. So here now we have an equation, y equals 0.55x plus 32.6. So this question actually asks about the height of fathers and sons. So given the height of a dad, can you estimate the height of a son? Which I think is pretty funny. So if I say I have some guy's dad and his height is 72 inches, can you predict the height of his son? So okay, my dad is 72 inches tall. I'm just going to erase some of this so I can then fill in the example. So in that case, I would do y, which is the prediction of the son's height, equals 0.55 times the dad's height, which is 72, plus 32.6. Let's just do that math really fast so we can figure out the height of this dad's son, which I know you're all very excited about. 0.55 times 72 is 39.6 plus 32.6 plus 32.6 equals 72.2. So for a dad of given height 72, and this is how you should try to frame your conclusions in a regression question. For a dad with height, see I before E, I always spell height wrong. With height 72 inches, we predict a son's height. I don't know which one is right. They're both wrong. Of 72.2 inches. And there you go. So that's how you do simple regression. You use a correlation and the standard deviations to find B. You use the means of x and y to find A. and you plug in an unknown. Well, you plug in a known x, and you solve for an unknown y. So I think it feels pretty straightforward. It's simple regression. Multiple regression, I think, has a lot of kind of curveballs, a lot of intermediate steps. So I can understand that taking much longer. Okay, so just to keep going through, I'm sorry if I'm pronouncing her name wrong. Malika? I'm really sorry. I apologize. So to answer your question, so that was an example of simple linear regression. Another question you have is, for the multiple regression analysis, the critical values of f come from where? So I mentioned this before, but I'll just say it again real quick so it's in everyone's head. Wow, and this camera angle is really bad, huh? This is going to be on YouTube forever, unfortunately. Okay, it's too late now. Let's keep going. So, right, so you have your f, which is r squared times n minus 3 divided by 2 times 1 minus r squared. Right? So in this case, the way you report it is f of 2 and n minus 3 degrees of freedom equals some number. So where do they come from? Well, the numerator, so this is a little backwards. The numerator degrees of freedom is always 2, which is this 2. And the reason why it's always 2, for you at least, is because we're only ever doing 2 predictors. So that comes from how many predictors you have. So in this case, for you, by hand, it's always going to be 2. Though it could vary depending on how many predictors you're using in your equation. But for all intents and purposes, for you, it's 2. The degrees of freedom for the denominator equals n minus 3, which is this n minus 3. So it's a little backwards when you're looking at this, right? The degrees of freedom for the denominator is coming from a term that's in the numerator, and the degrees of freedom for the numerator is coming from a term that's in the denominator. Don't let that fool you. The degrees of freedom, when you report it, will always be 2 and then n minus 3. So you can think of it like n minus 3 is kind of like big N minus k, which is the degrees of freedom within in an ANOVA, right? They are related. We don't have to go down the rabbit hole as to why they're related, but they are related. So the fact that you have a big N here should be a tip-off. Oh, big N, that's probably thinking about overall variance among everything, among all groups, right? This will always be a bigger number than 2, which should make sense because in ANOVA, as well as with multiple regression, you're dealing with Fs. You're dealing with kind of 2 sets of variance. One is the variance between, and one's the variance within. So this is kind of like your degrees of freedom between. Kind of. And this is kind of like your degrees of freedom within. So that's where they come from. They come from here, where it'll be 2 and n minus 3, and that's how you look up your critical value. The same way you would in ANOVA. You have 2, and you have some value of n minus 3. You'd use both of those to find the critical value, and then you compare your f, which is related to your multiple r, to the critical value. Okay. So that's where they come from and why they are what they are. So let me go back. There are more questions. 3. For the effect size of multiple r, do we square big R or the little r's that we found from the first step doing Pearson's R? Okay, so when you want like the effect size of all the IVs together, like how much. So if you're at the review yesterday, I talked about something called the pi of variance, which I will draw. like this. So think of it like an apple pie, but it's variance for your outcome. So this is like pi of variance in y, your outcome. And I have two predictors, and they each want a slice of this pie. So like this is IV1, and we'll say this is IV2. So perhaps they overlap a little bit. And you'll realize this based on the correlation of IV1 and IV2, that maybe they are addressing the same bit of variance in y. And that's okay. What big R is going to do is kind of tease that out and figure out kind of how much of a slice are you taking out of this pie with both IVs. So if you want the effect size, in that case, it would be big R squared. It's telling you kind of the percent of variance being accounted for by your IVs. So the R squared. It's much nicer drawing a pie of variance on the computer as opposed to on chalk. So in case you want to draw it at home one day. Okay, next question. For the post-hoc 2-keys test on two-way ANOVA, I know that this is only to be done if there are 3 or more levels. Perfect, that's good. But if there is not 3 or more levels, do I just find the significant differences based on which F's were accepted or rejected? And then the F's that were rejected is where the difference occurs, and if it occurs when there is an interaction, then that interaction is the difference, and I can tell based on the number differs the most from the others. Yeah, so that's mostly right. I'm sorry if I mumbled a little bit at the end. So I'm going to erase here. Okay, so just to kind of clear all that up and put it into straight, coherent things. Okay, so you have a two-way ANOVA. Which means you have two predictors, two IVs. Let's say height, and let's say running speed are your predictors, and your DV is I don't know, some happiness scale. No, I'm sorry. This is like a setup for a regression. What I want to say is I have grade, and I have, let's say, hunger. And this is rated, this is either starving, sated, or full. And grade is either first grade or 10th grade. Right, so this is a 2x3 ANOVA, where this is grade with 2 levels, and this is hunger with 3 levels. So the question that comes up is 2 keys if only there's 3 or more levels. But if there's not 3 or more levels, I just find the significant differences based on which F's are accepted or rejected. Yeah, so if they were both significant, right, you do an F for grade and an F for hunger. If they're both, if you reject the null for both, you would want to do a 2 keys for hunger because it has 3 levels. For grade, you don't need to do 2 keys because it only has 2 levels. If hunger was not significant, then you don't have to do 2 keys. If grade was not significant, then, and hunger was, and you still have to do 2 keys because it has 3 or more levels. So anytime you reject a null for F and your IV has 3 or more levels, you do 2 keys. If it only has 2, what the F is telling you is that there's a difference. And if you only have 2 levels, then it must be the difference between those 2 levels. There's no other place for a difference to reside. It can't hide somewhere. It must be between those 2 levels. So in this case, for grade, if this is happiness, as is my IV, then I have 2 distributions, a happiness for first graders and a happiness for 10th graders. The F is telling me there's a difference, which means it must be between these 2 groups, these 2 levels, first and 10th. If it was 3 levels, like first, 5th, and 10th, then what is it? Is it between those 2? Is it between these 2? Is it between those 2? Where would the difference be? That's why it's 3 or more levels, because then there's more than one option as to where the difference could reside between your levels. But when it's only 2 levels, there's only one possible place for there to be a difference. It's between those 2 levels. So that's why you only do a 2 key with 3 or more, and why if you only have 2 levels, you don't need to do 2 keys. You could do a 2 keys HSD, and I would bet you $1,000 that your mean difference would always be greater than the 2 keys HSD. By definition, that's what should always happen. I would bet a lot of money on it. So please don't do it, because you're going to waste time. You're not going to gain any information. It's much easier to say, oh yeah, 2 levels, I know where the difference is. And then she goes on, if there's an interaction, the difference, and I can tell based on what number differs the most from the others. That's usually a good way to tell. So let's give a few interaction examples. We can use the one from the second exam, and we can do a different type of interaction as well. So the best way of trying to figure out your interaction is just by looking at the data. So remember on the exam, we had men and women, and we had managers and workers. And they rated their opinion of some sexual harassment training, right? So the male managers rated it 8.8, the female managers rated it 8.9, the female workers rated it 8.6, and the male workers rated it 6.2 or something. So what you should see here, just by looking at the data, is that everything is very similar except for male workers. So if you were to draw a graph of this, let's say here we have men, and here we have women. We have a graph that looks like no, I'm sorry, I drew this the wrong way. If we had workers, management, then for women, we have something like this. And for men, we have something like this. Right? So this is the 6.2. And then we have 8.8, 8.9, 8.6. Right? So what's driving the interaction? Which means that there's a difference here, but not here. It's the men. It's the male workers. So that's one type of interaction that you would look at just from the data. Another type would be like a crossover interaction that you would also be able to spot from the raw data. So in this case, let's just use the same example and just change the data. So we have management, we have workers, and we have men and women. And let's say the male management thinks this training is great. The male workers thinks this training sucks. The female management thinks this training sucks. And the female workers thinks this is great. So So here you can see there's kind of a flip-flop between the two, right? So again, if you were to draw it, where you had workers and management, you could draw for workers. So let's draw men first. So male workers think it's low, and male management think it's high. So we have 8.8 and 6. This is for men. Whoops, I don't know why there's a line there now. And then female, let's X that out. Female management thinks it's low, and female workers thinks it's pretty high. Here we have 8.6 and 5.9. So this would be a crossover interaction. That's because the two kind of groups cross each other in the middle here. So, right, so if you have an F of an interaction be significant, first of all, you can't interpret the main effects. So if you have significant or non-significant main effects, it doesn't really matter if you have a significant interaction. And from that interaction, the way you would kind of make a conclusion, like you wouldn't do a 2-keys because the levels don't make as much difference as the interaction between the two IVs, you would then have to go back and look at your data and find the relationship. So that's how it works with interactions and kind of what to conclude. So I think those are all the questions from emails. Chat has been very quiet, so it would be great if anyone had any other questions. We have another 13 minutes. So if you do have a question, I would be happy to take it now. The test is on Monday, so you have a few more days to study and review everything. So I will just leave it to you guys for a few moments for any questions that come up. Just put it in the chat. That would be good. Or if an email comes up between now and 3:30, that's fine too. So you tell me what you want to talk about in the next few minutes. Or not. Or you guys are totally prepared and you're ready to just tackle the test when it comes. And in that case, I think that's great. So I'm going to look through the book while I wait for someone to ask a question. I guess to prompt you for a question, I will talk more about Fisher's Z, because everyone seems to ask about it, and I think it's kind of a silly topic, but we'll talk about it. So in this case, Fisher's Z. Is it Fisher's Z? Yeah, Fisher's Z. So why are you going to do this? You're going to do it to compare two correlations. Are they different from each other? That's your question. The null hypothesis is that they're probably not different from each other. The alternative hypothesis would be that one correlation is stronger or weaker than the other. So what the equation is, for everyone who's curious, and you can put this on your formula sheet if you'd like, is big Z equals the Z of R1 minus the Z of R2 divided by the square root of 1 minus big N 1 minus 3 plus 1 divided by big N 2 minus 3. So this should look kind of similar to a t-test, right? It's a kind of a mean difference divided by the square root of some measure of variance that's based on sample size. Remember that standard error of the mean and the standard error of difference at the end of the day comes down to units of the square root of n. So having something in the units of n in the denominator should not be super surprising. So basically, you have to look up some of these values. You have to look up this value and this value out of the table. Which is 11.4 in chapter 11. I mean, you could calculate it. It's this crazy calculation with logs and natural limits and stuff. Both logs and natural logs. No, just natural logs, I'm sorry. You won't have to calculate logs on the test, so don't worry about it. And then this is just the number of people you have. So you look these up, because you'll have like a ZR. So for example, I'm sorry. If your first correlation, let's say R1 equals 0.2, you go and look up 0.2 in the book, and that equals a Fisher's Z for R1 equals 0.203. Let's say R2 equals 0.4. That equals a Z of R2, and I'm just looking out of the book here. 0.4 equals a Z of 0.424. So those are the numbers you would use in your calculation of Fisher's Z. So we can just do that real quick. And I'm only doing this because no one's asking a question. You think I want to do Fisher's? Oh, finally, Sarah, you asked a question. Thank you. But now it's too late. I'm doing Fisher's Z. I'll ask in 1 second. I'll answer that in 1 second. So here you do 0.203. See the kind of torture Fisher's Z is? It gets people asking questions about anything other than Fisher's Z. So these two numbers that I looked up, divided by the square root of something that's going to have n. So let's make up some n. So I'm looking here at page 307 in the hardcover book, and there's an example that uses an n of 100. So this divided by the square root of 1 divided by 100 minus 3 plus 1 divided by 100 minus 3. And that gives you some value. Let's just calculate it. 0.203 minus 0.424. So this is negative 0.221 divided by the square root of 0.01 plus 0.01. And that equals, if you do the math on that, that equals 0.141, 0.221 negative. So divide that by 0.141. And you get a Fisher's Z of negative 1.56. Now, since Fisher's Z follows the Z distribution, then you know the critical value at an alpha of 0.05 is 1.96. And so since your calculated value of negative 1.56 is not as extreme as 1.96, then here you would fail to reject the null and say that the correlations of 0.2 and 0.4, where your big N is 100, are not significantly different, or probably not. HO is accepted. So it's probably not different. So that's how you would do Fisher Z. You take your correlations, you look up their analog in Fisher Z in the table 11.4, and then all the other information you need is just your total number of participants, your large N, and then you just plug them through. And that's to see if there's a difference between two correlations. Okay, now with that out of our systems, let's answer Sarah's question. Are all the tests interval ratio scale besides chi-square, which is nominal? So let's see. Z-test, yes. Single sample t-test, yes. Independent samples t-test, yes. Chi-square, no, like you said. Correlation, yes, they have to be interval ratio. Paired samples t-test, yes. ANOVA, yes, because you have to deal with mean differences. So you need means and standard deviations. So you would be dealing with interval ratio data. That's true. And regression. So regression, you can use either. You'll often see it with interval ratio, but it's not exclusively interval ratio. You can also use nominal data in a regression as well. So the answer for that is both in regression. So everything but chi-square and regression, which is both, is the answer. Any other final questions in the final 3 minutes before we go our separate ways until the final, which I believe is Monday? I will see you there. I will be proctoring the exam, so make sure for the exam, so I'll put all this down in writing so no one has an excuse that they didn't know. These are the things you need to bring. 1, bring a calculator, please. 2, your textbook. Super important to bring your textbook because it has all of the tables in it. So if you need to look up a critical value, you need your textbook. The other great thing about your textbook is that the computational part of the exam is open book. So if you blank out in the middle of doing a question, you can just flip to that chapter and look at it. So that's fine. Like you have tools at your disposal. 3, formula sheets. For the final, you get 2 8.5 by 11 front and back. Tomorrow, no, only the computational. So I'll explain how the test sequence will work in just a second. And on your formula sheet, and I brought this up in person too yesterday, use it to its full extent. You get 2 pages to put wherever you want. Don't just scribble in a few formulas. If you need to have an example of how a question's done, put an example. If you need a definition of what something means, put it on there. Use it however you find best for your test-taking style or for what you find is a weakness when you're taking a test. Like, do you always forget what is the measure of variance for this test? Put down. Standard error of difference is the measure of variance in this t-test. Like, that's fine. So really do spend the weekend to really hone in the information that you're bringing with you to help you when you test. So Tamar, the test, the way it works is that you'll take the conceptual first, which means all your things have to be put away. No textbook, no formula sheet, no calculator, no nothing. Just pencil, Scantron, test. Those are your 3 things. You can take as much time as you need on that conceptual. When the conceptual exam is finished, you'll turn that in. When you turn it in, you'll be given the computational version of the test. So you'll get computational. So then you have the remaining amount of time to do the computational portion of the exam. At that point, you can then take out your book, take out your calculator, and take out your formula sheet. So then you'll have the remaining time to finish. The conceptual exam is the same length as it's been. It's 50 questions, multiple choice. And the computational has between 6 and 8. So it's only open book for the computational. And the length of time for the conceptual should be the same as it's been. So, as a proctor, I can say that most people finish the exam 1 and 2. They've finished the conceptual before an hour and 20 minutes goes by, right? Your usual test taking period is an hour and 20 minutes. So usually most people finish before the hour and 20 minutes is done. It's very rare that people are still working up until the end for the conceptual. So think about how long you've taken for conceptual exams 1 and 2, and that will probably be the amount of time that you'll take for the final. They are both cumulative, about a third from exam 1, about a third from exam 2, about a third new material, which is regression. So as I've been telling my students over and over, a 66% should be like the lowest you get, because you've seen the material before. We've reviewed the material in office hours. We've reviewed the material here in these reviews. So like t-tests, z-tests, correlation, ANOVA, you should feel pretty good in. And if you don't, please email me, and we can continue to go over it until Monday. So I think really you should be able to nail 2/3 of this final, since it's all stuff that you've been tested on before and we've been able to review in depth. So I think everyone will get 100, so aim for that. And with that, I think we're at the end. So please do email me if you have more questions or something comes up between now and Monday. I've really enjoyed having everyone in recitation, and the people who haven't been in our recitation I've enjoyed talking to as well, who have come to review. So good luck studying, good luck on your other finals. Make sure that you are allocating time appropriately for all your finals. Don't let this one tank you on some other class. Take it all in stride, and I will see you on Monday during the exam. Remember, it's in the physics building, the physics lecture hall, which is near where your other tests were. It's right next to where the other tests were. So make sure you know where you're going and you don't get lost. Okay, have a great day. Have a good weekend. See you Monday.